Thanks a lot. Let me start by thanking the organizers for setting up this very nice event, and thanking ICTS for always the warm hospitality. So the story I would like to tell you today is about magic. So I thank, first of all, also the Bhattacharjee for deconstructing the word before me. Okay? And it's a joint work with many people, and in particular the stuff I will be presenting today is with Martina, Poetry, Emanuele, and Mario. Okay? So what is the question that we want to address? So suppose that one day somebody comes to us and say, okay, we have a fully working, error-corrected quantum computer. Of course, this is not the solution to everything. We want to know how much the resources that the machine has scale if we want to realize a certain quantum state. So, and in particular, we would like to have an interesting quantum state, like a critical state or a state which is relevant for gauge theories that Bhattacharjee was mentioning about, so something which is strongly correlated. Okay. So how can we quantify this? This is the basic question. Of course, the naive answer is, well, of course, isn't entanglement enough? And of course, the answer to this question is absolutely not. This is trivially not. And in condensed matter, we have seen applications of states which have infinite entanglement. I mean, these are examples in these Clifford circuits, that you can simulate straightforward in a classical manner, so with polynomial resources. So it is clear that in terms of characterizing the difficulty of a target state to be represented on a quantum computer, entanglement cannot be the full story. Okay? In principle, entanglement alone, it's absolutely uninformative. Okay? So now we can try to draw a very sketchy and by far not rigorous complexity diagram. Okay? On one axis, we put entanglement, lack of separability. So, and we know, and there has to be another axis. Because they know that there are states that lack a property, okay, which are always simple to simulate, but there will also be states which do have some of these properties, and since they have a lot of entanglement, they might potentially be hard. Okay? So this talk today is about this axis. Okay? This is, of course, relatively understood. I mean, we have seen also yesterday several talks, including one by the chairman, about how much is known about entanglement in many body states. We want to see this other direction. Now, in order to understand how to answer this question, is this good to have a look at how a quantum computer works. And of course, I'm not a quantum computing expert, so I will tell you a very simplified story about it. Okay, so a quantum computer you can define in two steps. I mean, first you have to have a problem target. Then you will have a quantum algorithm that tells you how you can reach the solution to the problem you're interested in with a given accuracy. And then from the quantum algorithm, you turn it into physical operation gates that at some point an experimentalist will go into the lab and realize. Now, in terms of error-corrected machines, there are many architectures, and by far the most popular one is called surface code. In condensed matter, this is sometimes called toric code, okay? Because it works with different boundary conditions. In gauge theory, this will be a Z2 boundary condition, Z2 gauge theory. Just to distill what this stuff does, it is acting on spin 1/2, and it is made out of this most popular kind of computing paradigm. It is made of two sets of gates. So one set of gates is on the left. These are Hadamard and phase. Whenever you see 2 times 2 matrix, this is acting on a single spin, so this is a single spin operations. And then there is an operation, which is the C0, which entangles neighboring spins. And then there is a new set of gates, which is called T-gate, which is just a local rotation, but you notice the angle, instead of being pi over 2, is actually pi over 4. Okay, so it's a very simple operation, it looks like. Okay, well, if you go into the deep of quantum computing, it turns out that there is a fundamental difference between having operation that work only on one set of gates and operation that include the T-gate. In particular, if you have operations only on the left, these are actually easy. What does easy mean? This does imply that performing error correction, so making the quantum computer work effectively, it is something which costs little resources. The guys on the right instead, they are hard. They're extremely expensive. So in fact, making a quantum error correction that works with this operation is much more complicated. And of course, you can also imagine that if you take this away, and you have operation value with this, which I want to emphasize, this is arbitrary entanglement. Okay? This is of course very easy because this is a Clifford group. Okay? So we can code it on the computer, very simple. Okay? So it is this T gate, which is the guy that we are interested in. Okay? The amount of T gates for a quantum computation, or actually for a given state, is what is called magic. There is also a more traditional word for this, is no stabilizerness, but I like, well, to some extent I like the word magic, even though it's confusing because it's also used in other fields of physics for different things, okay? Which has nothing to do with. So how do we quantify this thing, this amount of T gates? Because at the end we want to quantify a state. I mean, we have an interesting state that we realize in a simulation, or we are just interested in, I mean, what is this magic? Okay, this is defined very simply. You take a given state that you're interested in, psi, you look at the circuit that derives this state, so the set of operations that derives this state, starting from a state which is in a trivial configuration. For instance, in spins can be all down, in fermions can be all zeros. And so the magic is the minimal amount of resources, minimal amount of T gates that you need to realize, that you need to input in to realize this state, period. Okay, this is really the definition. Now, let's go back to our complexity phase diagram. So now we have another axis where we can say, okay, there is magic here. And if a state has a lot of magic, but little entanglement, we will use tensor network. If a state has whatever entanglement we want, but very little magic, we will use some other algorithm based on this, on other operation, which is called Pauli computing. States in the middle instead are hard, okay? But of course, the problem is, do we know if a state of magic we are interested in has magic or not? Okay? With entanglement, we know the answer to this question very well. Okay? Yes?
I'm completely confused. Here for the second time.
Sure, no worries.
So if I go to the x-axis,
Yeah.
this is supposed to represent the strength of entanglement.
Correct.
Now, there are at least two ways to measure the entanglement. First of all, whether it's area law or volume law.
Okay, we're talking about pure states, that this is important. And here I'm just putting whatever entanglement. This can actually be true in any dimension, what I'm saying. Think about one dimension for simplicity. Here, you imagine that you have states which has volume law entanglement, almost maximal entanglement. If they have very little magic, they are extremely simple to compute.
So the entanglement here is area law.
No. It can be here 0, then middle area, and then it's volume. This can be volume.
But because even if I restrict myself to area law,
Yeah?
I can have weak entanglement and strong entanglement.
Correct, you're right.
If I have
You're right.
volume law, again, I can
Yes.
play with the coefficient.
Yes.
This
axis has everything. This axis has really everything. So here there will be 0 entanglement. This will be area weak, area strong, volume weak, volume strong. So here you imagine this is the maximal possible entanglement you can realize given the number of qubits that you have.
And you are saying that the other axis has nothing to do with whether I'm area or volume?
No, in principle, no. We will see later on that there might be constraints between these two axes, but these constraints are not generic. No. What I mean is that this axis here, if I have little magic, the complexity is irrespective of entanglement. So it is always easy. So maybe this is, the easy is also here, of course. Sorry? I cannot hear. I will show you. Until 2022, this did not exist. Questions? Okay, I know that the topic is a bit weird, so please feel free.
It's obviously not sufficient that the system is area law entanglement.
Yeah. I mean, let me also mention that even if you have both of them very large, here I'm putting hard order with the question mark, because when we are talking about computational complexity, of course, there could be some other algorithm that nobody is aware of that can realize, can sample this state efficiently.
Where do integer polynomial states belong?
We do not know. Do you know the magic?
I don't think it can be produced by quantum.
This is irrespective of magic. Does not care about this, because magic you can have an infinitely deep circuit, but if there is no T gate, this is infinitely simple. Okay? So that's why it's a concept that is not really related to depth. It's related to the specific resource that you put into the depth of the circuit.
To clarify, you can have infinite circuits around.
Yes, it's no problem. Because for a quantum computer, they are not expensive if there is no T gate. Okay, good. So let me say, I mean, this is of course theorist motivation, but let me also mention that there has been experiments, in particular in the group of Micheluki, that really took the first steps in trying to address some of the quantities, these magic quantities we saw today. And what they wanted to show in their experiments, I think is extremely impressive, is that they can realize states which have both large entanglement and large magic. And these are these two plots, which is of course the last figure of the paper, where they have the entropy versus subsystem size and the magic versus depth. And they saw that both of them become large as they operate more on their circuit, okay? This is really, if you want, in resource theory, this will be bell pairs, this will be T-gates. So this is just to mention, this is the only slide where I mention experiments, that this is not only theorist wishful thinking. Okay. Now, we know about magic. I mean, whenever we have a quantum resource, there are three questions, in my opinion, that shall be addressed. I mean, of course, the first one, of course, is also motivated by the previous question, is how do we compute it? Okay. The second is this quantity actually related to physical phenomena or not? This is not clear. And in case we can understand these 2 points, can we actually exploit this quantum resource to design better classical algorithms to simulate physical systems, which overpower existing methods? Okay? So, and of course, there are many works in the last year and a half about this, and I will mention some of them in the following. Now, if we try to look at these same 3 questions, and we are in the early 2000s for entanglement, and we look at the future, I mean, of course, we see that this has been answered subsequently. I mean, think about how to compute it. First, this was in terms of observables, then in terms of methods, and all of these were addressed. Is it related to physical phenomena or not? We have seen yesterday from the chairman talk, a review of this. I mean, of course, this was then showed that entanglement in certain cases is related to physical phenomena. These are just some examples. And also this was shown to be useful to push the boundary of numerical simulation. I mean, somehow, within magic, we do not know much about this story, and maybe at some point there will be failures. Okay? Now, okay, maybe this is a more of a quantum information inspired thing for those of you that are coming from that community. You can imagine the comparison between magic and entanglement in a very simple manner. So in both magic and entanglement, there are some free states. And for entanglement, this will be separable states. But for magic, this will not be separable states, but will be states which are stabilizer. So there can be arbitrary entanglement. The free operations in entanglement are LOCC. In magic, this will be what's called Clifford operations. So this set of gates that I showed you before. The resource is very different. Entanglement will be bell pairs. In magic, it will be T states. And the measures for entanglement, you know, for instance, in pure states, we have the Feynman entropy. And here, big question mark for the moment. Okay? So now, this is the outline of what I would like to tell you in the rest of our time is, first I would like to show you how do we compute this thing. Okay? And then I would like to show you some examples in terms of physical phenomena, whether magic can play a role, particularly in the context of quantum critical behavior. And then I will show you that in certain cases, there is a connection between magic and entanglement, which is rather subtle. And finally, I will show you how this can actually be utilized to push the boundaries considerably of numerical simulations based on tensor networks. Okay? So the first thing is we want to compute this thing. Okay, this is. But it's already clear from the definition this is not going to be an easy journey, because if we go back to what we were saying, this is the minimal amount of resource. Whenever there is minimal, I get concerned because it implies there is some sort of convex or maybe not convex minimization. I'm really scared. So it's like a story of this guy that tried to dunk by putting his arm in front of it. I mean, you don't know how the story ends here. You can go and watch this video on YouTube. This guy is D. Brown. It's actually a funny video to look at. Yeah? So, but we do not know at the beginning, I mean, a priori, because this is a minimization. Okay? And the second, even if we find a quantity which does not require minimization, can we actually compute it? Okay? This is not clear. Not clear. So this is, again, this non-convex optimization problem. And luckily for us, there were people from the quantum info community that were able to solve this problem. I mean, this magic has been known in terms of resource theory for quantum computing since 2005, the work by Kitaev and Bravi. But it took many years to have something which is, in my opinion, of very, very practical use. This is a called stabilizer Rayleigh entropy. And what is this formula? I mean, given a state rho, that for us will be pure, this is essentially an entropy, but here, what you see, you have the trace of rho times p, and p is a Pauli string. So you have to take the expectation value of all Pauli strings and get this observable. This is an entropy. From the condensed matter viewpoint, yes?
So this magic measure is a measure of the amount of magic you need in order to prepare the resource state, or the amount that you need in order to, once you have it, to manipulate it?
No, the first, to prepare it. Yes, to prepare it. What is important here is that, I mean, in condensed matter, I wanted to mention this, you can also see as a, essentially, participation entropy over Pauli strings. That's another way of seeing that. Now, let's scrutinize this thing a bit more. I mean, it looks very nice. It's formulated as expectation values, satisfies the property of a measure, pure states, is probabilistic, so for us it's pure gold, but there is still a fundamental problem, that this sum is overall the possible Pauli strings. Now, on each side of a spin chain, or a spin model, I have four possible Pauli, sigma x, sigma y, sigma z, and the identity. So this implies that the number of measurements that this tie requires is 4 to the n. So even for exact diagonalization, this would be extremely hard to measure. Yes, please.
When you say strings,
Yep.
they mean all Pauli words on lattice?
Correct. All of them.
Okay, not strings as in one dimension.
No, not strings. This is really combinations. Okay.
Pauli words.
Yes. Yes, that would be. Capital N is the number of spins, and D is the Hilbert space dimension that for spin 1/2 it will be 2. But of course, this you can define for arbitrary spins. Four. Yeah. This 4 Pauli matrices. No, 4. The identity is also considered an element of a Pauli group. Yeah, of course, the identity you don't. You can do that, but this does not simplify. No, I mean, the number of expectation value you have to take is still the same. But it can be done. I mean, if for some reason it's practical, then you can do that. No.
Can be interpreted as unit or some non-local operator, expectation of some non-local operator?
There are arbitrary local operators here, of course. Okay, this is there are Pauli strings of a single bit, then until the n, and you don't know a priori which is more important, which is not. This was a question about the Pauli spectrum, which is a equivalent of entanglement spectrum, but I'm not going to talk about it. Okay. For what I'm saying today is only pure. Yeah, I mean, there is one Pauli matrix, which is the whole identity, which is the purity rho square, and this is 0. But the rest, so if you want, this is, that's why I have not put 4 to the n. It's 4 to the n, then there must be minus a constant that depends on the symmetry. Yeah, the purity point, then if you have U1 symmetry, there is a bit less, but so that's the scaling. Good, so how do we compute this beast? It's not so clear. Not even for exact analyzation we know how to compute it. And, yes, please.
Does it have a intending to one limit, like the one and stuff? Or
Yes, it does. It's called linear entropy, and is well defined. Yeah. So how do we compute this thing? And so we formulated two approaches to do that, but I want to mention that there were other works which I find very interesting, also before ours, by Haug, Piroli, Lamy, Collura, and Piroli and Haug, that also tried to formulate methods to measure this quantity in tensor network simulations. And I want to emphasize all these methods are extremely simple. So they're not fundamentally complicated tensor network techniques. These are really straightforward. So one is essentially we have tried to map the computation of this Rayleigh entropy into a new tensor network computation, so to conduct a new transfer matrix. I'm not going to discuss it today, but it's nice because it does not require any sampling. And instead, the other one that I would like to tell you briefly today is based on the fact that we have a probabilistic interpretation of these objects. Okay? It's called, and we try to use what is called Pauli Markov chain. So let me tell you very briefly. I mean, these are the four people that did that, and I could not resist this picture that we fit in an old school 500, and the old school 500 is smaller than an auto. Okay, so it is really a very compact situation. Okay, so what we try to do is the following. I mean, given that we have here probabilities, kind of, something it looks like probabilities, instead of sampling the state, why don't we do a Markov chain on the space of stabilizers, okay, on something which is defined as rho times p. And we do it with importance sampling. Does it work? We do not know, okay? But this can be done in principle both in experiment and theory. So let me write down the algorithm for that. Okay? So we start with a Pauli string. For instance, we have a system of 4 spins and we take sigma x of the second spin. Then we measure its expectation value, and then we propose a new Pauli string. This can be sigma x, sigma y, sigma z, with some rule. And then we check the value of this. Is the value of this smaller or larger? We compute it, and then we check what is the relative ratio, like we will do in a Monte Carlo simulation. Okay? If the relative ratio is larger than 1, we accept the new string, otherwise not. This is somehow we are doing a Markov chain in stabilizer subspace. Now, this satisfies detailed balance, it's straightforward. Of course, like in any Monte Carlo simulation, there are fundamental properties that have to be addressed. So whether this is ergodic, this is straightforward ergodic, in the way I formulated it. Are the estimates reliable or not? This is not clear. Can we actually do it in a tensor network? Are there efficient tensor contractions? Or there are memory effects? So all these things have to be checked. And it's not guaranteed that this is actually a practical algorithm. And the way we did that at the beginning... Sorry, what is what? Oh, this pi of p is the probability associated to a string. And if you want, it is equal to this trace of rho p to the 2n. So this is maybe the only unpractical thing. So you have to select a rain index before doing a Markov chain. No. Yes? No, then it's... No, well, actually, but it's not only this. That Pauli computing work only if you have a very, very little magic. Here we want to have a measure and an algorithm that computes magic for an arbitrary state, where Pauli computing will not be applicable at all. This is important. Okay? So we're not going to do it in Pauli computing. Yes?
So when you compute the trace over there, is it, if you have a generic quantum state,
No, it's not easy. No, it's not easy. Okay? You're right. So actually the first thing we tried, because we wanted to, since we are manipulating now arbitrary non-local objects, we want to have a tensor network structure which accommodates easily what in Monte Carlo will be non-local updates. Okay? And the best tensor network structure for this is trees. I just don't want to spend too much time on this. I mean, but what we can do these trees, we can show that doing these contractions is actually proportional to chi to the 4th. This is the bond dimension of the MPS. But importantly, the dimension of the system size is logarithmic. Okay? So doing this in any dimension has the same cost, up to a constant. That's why we found it very practical. Okay, you don't want me to go over this, I will not tell you. Okay? If you're interested, we can discuss on the blackboard later how we do these contractions. But the point is that now we have methods, which are either stochastic or exact, to treat magic in many body systems. So now, can we learn some physics? Or maybe we will learn that magic is irrelevant for physical phenomena. We do not know. Okay? And the first thing we tried is critical points. Okay? So we have a lattice model, which undergoes a phase transition from an ordered to a disordered phase, something very simple. And these are some examples of the magic density as a function of the external field in what is a called three-state clock model. This is a model which undergoes a transition from an ordered phase here to a paramagnet here. And the different points represent different volumes from L equal to 8 to under 28. And one can see that already at the qualitative level, it looks like magic is showing us the correct physical information. So it shows a peak very close to the transition, which is here, it's in the very proximity of 1. Okay, you can tell me it's a qualitative approximation, who cares? Okay? If you want to show that this is related to criticality, you have to do something better. And here what we have done finite size scaling, so collapse scaling, with critical exponents nu and gamma of this quantity of these experimental observations. And one can see here from the quality of this collapse that this is actually capturing critical phenomena in a correct manner. And also the critical exponent nu is the same of the correlation length. Yeah, the transvestite model was actually shown already before us by Haug and Piroli, that this also corresponds to the nu critical exponent. Okay. The interesting thing, I mean, they did all the study on this. The problem is that their algorithm was very expensive because in MPS was constructing an 8-state replica to measure the magic, and this is, you can do only for very small bond dimension. So you could not do something like a three-state clock model. This is really something we could do only with these new algorithms. Okay? So the full state magic is sometimes informative about scaling. But then we did the same simulation for another model. The details are not important. It's a spin one chain that undergoes two phase transitions. In the middle, there is a topological phase. These are just two phase transitions. And here, the magic does not care at all about phase transitions. You see, these are very smooth curves. The full state content seems to be completely undetermined by this quantity. So this implies that one has to be careful in analyzing these things. So, and the thing we try to formulate is, well, let's try to do it like entanglement. I mean, it could be that this magic also has the problem that there are non-universal effects due to boundaries, areas, and volumes. So let us formulate a mutual information of magic. Okay? And this is a quantity. Essentially, we take the magic of two partitions, A and B, which are disconnected, and we subtract it from the magic of the partition A and B. And these are the same results, same model. This is the total magic, which shows nothing. And this is instead this mutual SRE, and this mutual SRE instead shows very clearly peaks at transition points. Okay? So this is teaching us that magic is related to transition points, but the relation might not be trivial. And in particular, it is not necessarily there in the context of magic of the full state, but it is there in something which is, if you want, lattice regularized. Okay? Something equivalent of mutual information. Now, this was only for CFTs and one dimension. You can tell me, okay, who cares? I want to live in a higher dimensional world. Well, then we did the same thing. Yes. Yes. For one dimensional CFTs, yeah? Let me be precise.
In the lattice phase of the suggestion chain,
yep.
we expect to track universal features in the entire space.
No, there, what we likely have is that we will have a large mutual SRE over the entire phase. Actually, we have computed it. Maybe I have it later in the talk. Mutual stabilizer Rényi entropy in the entire Lattinger phase, and then it can go lower, for instance, in the antiferromagnetic phase, because this is a stabilizer state.
In the lattice phase, we expect all of them to converge to
no, probably, well, there will be no peak there. There will be a peak at the BKT point.
But it will be universal.
Yes, it will likely be universal. I mean, to do the now I'm saying what I expect. To do the computation, I do not know. Because, of course, if you want to see BKT physics, you have to go to huge volumes. And I do not know what the finite size scaling theory for magic is there. Yes?
So when you look at the three-state
Potsman.
so you see the finite size scaling, right? So
Yes.
Is there any relation with the magic with the susceptibility?
Well, the critical exponent nu is the one of the correlation length. So if you want, there is a relation, but the gamma, it's a number which it's not clearly related to any. Yeah. I mean, yeah, I don't want to make strong statements about this. No, this can, okay, this is interesting. If this SRE was a measure of magic, this quantity would have been positive definite. It is not, because as I said earlier, this is true only for pure states, okay? Now these are mixed states, so this is not a measure of magic anymore. This is more a measure of mutual inverse participation ratio of this stabilized subspace. So the physical interpretation is slightly different. Okay? If you want, with entanglement, the equivalent is if you do the mutual information with the Rényi 2 entropy. I mean, this is not positive definite, because it's not a measure. No, it has to be large. What we typically do, we do L over 4, L over 4, L over 4, L over 4. Because this keeps all the symmetry into consideration, and we use periodic systems. So now, I mean, I was very interested because one D somehow is very close to my heart, but then one of my younger collaborators said, no, we have to show something for 2D. Okay? And what we did the simplest model of relevance is Z2 gauge theory. So we have here the magnetic field and here some external electric field. So this model has a phase transition, there is a spin liquid, here is a paramagnet. So this is the magic as a function of this parameter H, which describes the Hamiltonian. The transition is 3.04, blah, blah, blah. It's computed by Monte Carlo very precisely. Now you can see these volumes are very tiny. Okay? This is 4 cross 4, 5 cross 5, until 8 cross 8. And you can see that all these curves cross at very close to the critical point, which at the beginning I thought the students were cheating me. Yeah? And then what I said, okay, do the finite size scaling, because then I want to see some discrepancy. And this is the quality of the collapse that you get. Okay? So you get the transition point with more than 1% accuracy and almost perfect collapse over a pretty large parameter space. I mean, how can it be? First of all, I mean, we also see magic does not always show peak. Sometimes this is a flex. And the collapse is too impressive. So what we did, let's try to compare it with the Binder cumulant. Okay? So this is the Binder cumulant with the same tensor network computation as a function of h. The Binder cumulant is crap. You cannot even say where the transition point is. The curves do not cross, blah, blah, blah. And this is the magic. So it looks like there is some very hidden power that this magic can have, at least in these gauge theories, which makes it more sensitive, both at the quantitative and qualitative level, to critical phenomena than the best thing we can think of, which is Binder cumulants. Okay? So there has to be some strange thing. Of course, it is possible that this is related to the fact that we are, in a tensor network simulation, we are only approximating a state. Okay? So this has to be related to entanglement. So what's the relation between entanglement and magic? Okay? And so to understand that, we took again our spin one chain. It's an Haldane model with single line anisotropy. The model is actually not important. We see the same physics in all the models we've studied. And what we tried to look at the convergence of both magic and entanglement as a function of bond dimension. Of course, entanglement is not. And what we notice is that for different critical points and different volumes, magic converge to its expectation value very, very quickly, typically with very, very modest bond dimension. For a critical system, it's 10. While entanglement, of course, requires parametrically larger bond dimension. Okay? And to do a more detailed entanglement scaling, what we saw is that this magic converges to the correct value with a correction which are inverse power of chi square. So this is really very, very quick. Okay? And let me say that the same was also found in random MPS. Okay? We do not know the origin of this for ground states. We don't have a theory. It's just for a moment an empirical observation which is true throughout all the models we studied. Okay? Now, what we have learned so far, magic is related to physical phenomena. Yes, at least in the context of critical spin chains and simple 2D gauge theories, this is true. And there is an interesting relation to entanglement. Now, since there is this connection between magic and entanglement, can we actually exploit this for better numerics? And then very naive thing is that since tensor networks are good at representing magic, maybe what you can do, we can dope them with Clifford operation to arbitrarily enhance their entanglement while keeping the magic constant, because this is already converged with a small bond dimension. Now, of course, we had this idea, but there were at the same time competitors that came with this idea before us, so I think they should get the credit. This idea of augmenting tensor network with Clifford operation really came in these 3 papers, and I will use the language of the second one, which is to me is the clearest. It's Clifford augmented MPS. Now, is the idea of augmenting tensor network with entanglement operations new? It is not new. In quantum information, this has been going on for more than 20 years. The first example is Mera. Okay? Then it turned out that Mera is extremely computationally expensive, but this is already insightful. A successful attempt was augmented trees. I mean, this really showed that one can do simulation beyond conventional trees. But in general, these other aspects are very generic, but they're also extremely expensive. Here, let's see how expensive that is, because augmenting something with Clifford can be very cheap. And the idea of these camps, this Clifford augmented MPS, is very simple. You take a matrix product state ansatz, and then you dress it with a series of Clifford operations. This implies that given the state that you have at the beginning, you can arbitrarily increase entanglement as much as you want, because you can put C-knots. But absolutely, you cannot create any magic. The magic has to be converged to start with. Okay? This is important. And people have done simulations with this, and the idea in a simulation, just for those of you that are familiar with tensor network, is that you can reabsorb this operation directly into the MPO. It's very cheap. And then you can do a simulation on a Hamilton, which is slightly non-local, but so the computational cost of doing this with respect to MPS, it just comes with a constant overhead. It's very simple. Now, can we actually, what are these states good at? This new class of state good at? I mean, are they parametrically better than MPS or not? Because if they're not, okay, maybe it's interesting, but up to some point. But if they are, then we can look at them for applications that are beyond MPS. I mean, this is a computational perspective, but I think this raises a deeper question. Is there a corner of the Hilbert space of entangled states in the form of MPS, which can actually be chopped with respect to its magic complexity, or this is not possible? Okay? And to try to understand this, what we did the following. We look at the procedure which is called local Clifford disentangling. So we take a state at the beginning, whatever wave function, it has to be matrix product state for us, and then we do the following sweeping procedure. We take, for each bond, we take all the possible Clifford gates, two-body Clifford gates which are allowed. In principle, this is 700, so it's very costly, but we found out that you can only use 20. If you do the things properly. And then we try to systematically disentangle the state by keeping a given Clifford. And we do it recursively. Okay? Of course, we do it locally because otherwise we cannot do the contractions. And then what is the figure of merit? I mean, we have started from a state which has a given entanglement. What we want to know is what is the entropy at the end of this. Okay, so we have this is the state that we have at the end of this Clifford procedure, this Clifford disentangling, and we look at the entanglement entropy of this state, and we look at the entanglement gain. So how much we have been able to lower the entropy with this Clifford circuit. This is the figure of merit. Now I will show you a couple of results. Does delta, I mean, what is important is, does delta increase parametrically with size or not? Because the entanglement will always be lower. But if it's lower by a bit, we are just doing MPS in a more complicated manner. Now, these are the results for the XXZ model at one value of delta, which I forgot, but it's inside the gapless phase. And here you find the entanglement entropy as a function of the system size for different values of L, up to a few hundred. And the bottom curve is the entanglement entropy, and the lower curve is this Clifford diminished entanglement entropy. Now, you can see by bare eye, both are log, but they look parallel. And an easier way to see that they are parallel, you look at the difference, delta, as a function of the same quantity here, and this approaches a constant, and notice also the scale here is essentially very small. So here, gain is a constant. So there is no parametric gain at all. Okay? You can do the computation with Clifford and MPS, you will have a bond dimension which is a bit smaller. You will have to do this minimization, so it's maybe not fundamentally convenient. This is another model. It's a model introduced in 2018 by Paul Fendley. It's a spin model, we don't care about it. What is interesting is it has a critical point in the critical easing universality class. Okay? And here you have the entanglement entropy, and this Clifford diminished entanglement entropy. Okay, now you can see that the two curves seem to have slightly different slopes. And actually, if you plot this delta as against a log, this is linearly increasing. So this implies that this Clifford augmented tensor network is seeing a new conformal field theory with a lower central charge. Okay? This is in principle great. Implies we can do simulations of much larger systems, or if you want much more accurately, with the exact same computational cost. Now, this is telling us that there is a new corner of the Hilbert space. Mm-hmm. Yes? Yes? No, this is true all over the phase.
So
yeah.
The parallel slopes feature.
Yeah, we don't see any particular difference. But later on I will explain why. Okay?
And also, what for the regular Ising control?
Oh, you will see for, okay, no, for XX, no, I've said something which is incorrect. For the XXZ model, if you are at the delta equal to 0, you don't see this. You actually see this. Okay, and I will show you why. Easy model, you will see the same instead. Okay? So, I mean, we have now numerical evidence that the Hilbert space is actually, of MPS, is not just a single corner, but is actually fragmented. So there will be states which can be disentangled with the Clifford operation, which is local. Okay? So this is for us really important because they can be simulated with a considerably lower complexity. And instead, what we call non-Clifford disentanglement, these are states where these camps, they don't lead to any parametric gain. So since the answer to this question is yes, I mean, are camps overpowering MPS or not? Okay, but I see my time is over. The idea is that the answer is yes. Okay, how much time do I have? 0. Good. Okay. So we want to understand the following. If the states are really better than MPS, there must be a physical property, like entanglement is in MPS, that guides the principle of this new corner of the Hilbert space. So what we look is the same mutual information that we had before. And the idea is the following, is that if these camps are able to work, what they are able to do, they are able to distill entanglement out of an MPS, but they have to do it in a manner which is not fully local. Because if it's fully local only, we will only gain something which is a constant. So there has to be some non-local correlation to capture that. So we look at this mutual stabilizer in entropy, and it turns out, these are the two plots. This is for the XXZ model, the gain as a function of JZ. The gain is always constant, and this mutual stabilizer is always positive, and whatever value it is, it doesn't matter. But for a tricritical easy model, it turns out that the gain is maximal at the transition point, and at the transition point, we have a negative mutual stabilizer in entropy. So for the quantum information people, this implies that we will be able to store a stabilizer qubit in a bipartition, but not in the single partitions. So there is really a form of correlation which is highly non-local that this new tensor network can distill. And can we understand it analytically? Yes. The idea is that you need models where there is an exact Clifford qubit, but in condensed matter, we know what these models are. Models that feature dualities. Dualities that have to be written as Clifford operations. Okay, this is just one example. If you took the easy, what is called cluster Ising model, this clusterizes in a number of Ising spins, which depends on the specific form of the Hamiltonian. For instance, in this case, this is 2. And if you look at, if you look at the SRE of the stabilizer thing, you will see a conformal field here, which is exactly half the central charge of your target model. Or even smaller if you have more powerful dualities. Good, conclusions. Take home, I think we are in an age where there are machines which are being developed that look at this error correction. And I think this motivates for theorists a viewpoint which combines our traditional condensed matter understanding, not only with entanglement, but also with this concept of magic. And we have some tools to compute it, and we have shown that this might be related, at least in some cases, to physical phenomena, and might be also used to push simulation. But of course, there are plenty of other questions, out of equilibrium, insights on now better quantum computations, more physical phenomena, and so on and so forth. So I think there is really very little explored because these new observables from quantum info are really less than 2 years old, so there is a lot of space. With that, I would like to thank again my collaborator, and thank you for your attention.
Let's thank Marcello for a very nice talk. We have a large number of questions, maybe a few.
This is a bit general question. So there is a very different paradigm of how to prepare or engineer states. And this has to do not playing with gates, be them magic gates or Clifford gates, but with steering.
Yes.
And one can have 2 levels of steering, passive or active, but let me talk about the more primitive and stupid one, which is passive steering. One can talk about steerable states and non-steerable states.
Yes.
And steerable states are states that are not frustrated in the sense that you can have, I don't have time to explain it, local parent Hamiltonians. I mean, you probably know that.
Yeah.
I'm sure. So can you
relate.
Say a few words about the relation between these 2 paradigms?
Okay. The relations are not explored. Okay? I will say that this is a problem not only for steering, but in general. So if you look at the pyramid of bipartite correlations, I mean, there is, of course, classical, discord, entanglement, steering, and Bell. And of course, each of them has different. So these are properties of bipartite correlations. Magic, if you want, is a property of the full state. And it is not clear that magic is informative about any of this. So I think it will be, I mean, there are actually some people that have studied in the context of 2-spin models where there are good measures of steering. the connection between steering protocols and non-stabilizers. They have not looked at the quantity we were looking at. They're looking at something else. I can give you the rest, but I don't know how much is known. There might be connections, yeah.
Srijit.
A clarification on the idea of CA-MPS. So are you saying that the state can be represented as a product of an MPS times a set of Clifford gates?
Correct. In this camps, yes.
And this can be used in the sense that time evolution becomes easier, or is it that?
Okay, with time evolutions, I have some doubts. This is important. I think these methods will at the end, they have potential for ground states and low energy computation or spectral functions.
The ground state becomes.
For time evolution, you see there is a problem. If you have a generic time evolution, the states very quickly becomes a hard state. Hard states, there is no way you can disentangle them with a Clifford operation. Okay? And in fact, in this in these papers, maybe I've not cited them, so I apologize. So there were some, these early papers that I mentioned, these were really more on the theory, but then, sorry, these references, these are the theory, but then the same groups have also tried to implement these camps with the TDVP, time-dependent variational principle, 1 and 2 body. And then they saw very modest gains. They saw some gain, but it's modest. And I think the reason is that, that if you have something which becomes R, it's going to be hard.
Yeah, Abhishek.
You defined magic as initially as the minimum number of non-Clifford gates required to prepare a state, right? And then you had another definition, like some measure of magic.
Yeah,
I mean, how exactly are these related? I mean, like.
Okay, no, this is the work that these people have done, which is non-trivial. They've been able to show that for pure states, this quantity is a good measure, so it's faithful, and it satisfies all the properties of a measure, is a monotone, and so on and so forth. No, it's highly non-trivial.
But how does it, if I really want to know the number of gates, how does it actually?
No, okay, these measures of magic, they give you always a strict lower bound. Then, if you want to say, I want to do a quantum computation, then you need to solve the problem of compilation. So you need to find not only the minimal number of weights, but also how they intertwine within the Clifford. This quantity is not informative about. You will have to look at other things. It's much more complicated.
Okay, Mani. Yeah.
Pure case, pure state. So given the two pure state, we have this Nielsen-Vidal kind of criteria under LOCC, state transformation criteria.
Yeah.
Something people try to explore in magic state also?
Yeah, if you want, it's a state, which is a resource-free state, so in that case, a stabilized state, its magic is invariant under the action of Clifford operations. Huh. So there is a perfect, I mean, if you want, in terms of resource theories, the tables that I put at the beginning, despite being simple, is already faithfully representing the status between entanglement and magic. Let me put it again. This one. Okay, so you replace a pure state with a stabilizer and the LOCC with a Clifford operation.
Marcello, one question from me. So, are there relations known between things like magic or, versus, let's say, the negativity of the Wigner function? These are.
Yes, this is, of course, where it comes from. I mean, there is a lot known in the context of continuous variables. Okay?
I see.
There is really, you can see, negativity of the Wigner function and magic are strongly related, which smells that also entanglement has to be related to magic. Somehow. Yes, you're right. For qubits, I don't know how much this relation can be put forward. I mean, this has been studied, but I just am ignorant about this.
Okay. Oh, thank you. Cheers. Any other questions? If not, let's thank Marcello for a very nice talk.